Friends, let us start our new session of chapter 14, Semiconductor Electronics, Materials, Devices and Simple Circuits.
Now let us understand semiconductor diode. So here, as you can see in the diagram A, the PN junction is available. With that PN junction, at the end metallic contacts are provided, which is connected with the external voltage. Here two terminals are there. One is positive, another one is negative, and this PN junction formation can work as diode. Here the direction of the current is flow from P type to N type material after applying external field. So that current is known as conventional current. Here as you can see in the diagram B, that is a symbol of the diode, which is defined in form of arrow. This arrow defines the flow of current in one direction from P type to N type in proper biasing condition. And biasing means to apply DC voltage. So here the equilibrium barrier potential is available at the junction. While we want to generate the current, so charge carrier is supposed to flow in complete loop. And whenever this barrier potential is existed, charge carriers cannot cross the junction and current cannot be generated. So here we need to provide sufficient external voltage between across this diode, so that barrier potential can be altered by giving this supply. So here two ways is how we can connect this supply. We can provide the biasing, forward biasing and reverse biasing. Let us understand first the forward bias condition of the PN junction diode. In the with the PN junction, while the external voltage is connected, that external voltage, for example, is denoted as a V. So positive terminal of that supply is connected with P side of the diode, and negative terminal of the supply is connected with N side of the diode, as you can see in the diagram A. So here this kind of provided biasing is known as forward biasing. This applied voltage will drop across the depletion region, and voltage drop across the P side and N side which very much less. Here initially, while we start to increase the voltage from 0, then current won't flow due to the depletion region. So here the resistance is offered by the depletion region from the center around the junction. So here this depletion region having no free charges and having a higher resistance compared to other side of the depletion region. Here this applied voltage is opposite to the barrier potential. So here, while we increasing this applied voltage equivalent to the barrier potential, so at that point its net effective voltage would be 0, which is known as built-in voltage or cut-in voltage. After that, while we increase the supply voltage, then depletion region width is diminished. So from the voltage, while we increase from 0 to built-in potential, depletion region width is gradually decreases and it will be 0 at built-in potential. So here the forward bias voltage we are having in terms of V0 minus V. So here if the supply voltage is small, then barrier potential is gradually reduced, which will give us very less amount of current, which is due to the minority carriers. So here the small number of carriers can get this energy level. These carriers can cross the junction and generate the small current in microampere. If we increase that applied voltage, beyond the barrier potential, then more number of carriers can energize and increase the current. That current, after built-in potential, the given supply will generate the current in milliampere. So due to this applied voltage, electrons from n side can cross the depletion region and can reach at other side in p side. Same way, holes from p side can cross the junction and can reach at other side, which is n side. So this process in the forward bias is known as minority carrier injection, because electrons will move from n side to p side, and in p side electrons can behave as a minority carriers. Likewise, holes in p side will transfer towards the n side, and holes are minority carriers for n side. So this process is known as minority carrier injection. Now, at the junction boundary on each side, the minority carrier concentration increases continuously compared to the other point of the junction. So due to this concentration of charge carriers, the electrons on p side diffuse the junction edge of the p side and reach at other end of the p side. Likewise, the injected holes on n side will diffuse from the junction and reach other end of the n side. This motion of the charge carriers on either side will increase the conventional current. Here, the diode having a current that is due to the total current, that current due to hole diffusion and conventional current due to electron diffusion. So here the current is existed due to both type of carriers, holes as well as electrons, having the current in terms of milliampere. So here, this is how the current conduction takes place while the PN junction is connected in forward bias. Now let us understand, if this PN junction is connected in opposite voltage direction, it means in a reverse bias, then how it will work. Reverse biasing, it means the given external voltage in which positive terminal of the supply is connected to the N-type semiconductor and negative terminal of the supply is connected with the P-type semiconductor, as we can see in the diagram. So here, this applied voltage is available across the depletion region. Now this applied voltage direction is the same as the barrier potential. So while we increase the supply voltage, barrier potential is also increases, which makes depletion region more widened due to the variation in electric field. So now the barrier potential in the reverse bias having V0 plus V. V0 is barrier potential, that is a built-in voltage, and V is the externally given voltage. So here, carriers cannot cross the junction and cannot move from N to P or P to N side. So here, the diffusion current will decreases compared to the forward bias condition. So the electric field of the junction, here we are having, if electrons on P side or holes on N side, they can get a random motion across the junction based on the minority carrier transmission, which will generate the current, and this current is available with the very low value in terms of microampere. This value is very much low because of the motion of minority carriers. So this current is compared to the forward bias having a low value due to the low injected carriers can cross the junction. This diode in the reverse condition is not dependent on applied voltage, because as the voltage is going to be very high, voltage drop across the junction will increases, but its current variation is not available. So here very small voltage is also enough to increase or to widen the depletion region, and accordingly the minority carriers can energize and generate the current. So here this generated current is not limited, is not depending on the applied voltage, but that is limited due to the concentration of minority charge carriers on either side of the junction. So current under the reverse bias junction is independent of reverse bias voltage, which is known as VBR, breakdown voltage. So here up to this breakdown voltage, current is independent of the supply voltage. After that limit, if we increase the supply voltage, which will cause the large change in the current. So if the reverse current is now not in control or limited by the external supply, and PN junction can destroy, which will completely destroy the diode, which we cannot use it further, and overheating start to produce. So here this condition also can be happen if the diode is in forward bias, and if we are continuously increasing the input voltage beyond its limit, then forward current exceeds its limiting value, then in forward bias condition also overheating will produce, which can damage the diode completely. Now let us understand its a VI characteristic. Here the circuit arrangement is defined in diagram A as diode is in forward bias condition. So battery is connected across the diode, which is connected with the potentiometer to vary the given supply voltage. Different value of the voltages we are going to note, and accordingly how much current will generate. So this data we are taking from the forward bias condition, and we are plotting these values on graph onto, as you can see in the diagram C, onto the x-axis we are taking voltage across the diode, and onto the y-axis current flowing through the diode. Here the positive voltage we are providing. So positive x-axis define the forward voltage, and positive y-axis define the forward current. Means forward characteristic is plotting on first quadrant of the graph. Here the generated forward bias voltage is available, that is across the diode. Silicon having a cut-in voltage around 0.7 volt. So up to 0.7 volt, the generated current would be very much low in terms of microampere. After 0.7, that barrier potential will reduce and depletion region width will diminish, so which can increase the current exponentially. So after 0.7, that cut-in voltage or built-in voltage, while we increase the input voltage, then voltage drop across the diode remains almost constant and current will increase exponentially, as you can see in the first quadrant in the graph diagram C. Now, if we connect the diode in a reverse bias, then generated current is very much small, around microampere. Here that given reverse bias voltage is negative. So accordingly, that reverse bias characteristic, the minus V voltage over the minus X axis, and generated current is negative, plotting on minus Y axis. It means the reverse bias characteristic is available on third quadrant. Now, as the voltage, supply voltage increases, all the voltage drop is available across the diode and very less current is available due to minority carriers in terms of microampere, as we can see in the diagram onto the graph. So here, as very higher voltage the reverse bias will provide, then breakdown occurs, that is defined as a VBR. After that, current will increases suddenly. So here, this is the general purpose diode is there, in which a reverse saturation current region is not going to be used after breakdown voltage. So PN junction diode allows the flow of current only in one direction, only in forward bias condition, where it offers very low resistance compared to reverse bias condition. This property of the diode we can use in many applications. Mainly it is utilized for rectifier, to rectify the AC voltages. So here this diode offers the resistance which is varying continuously by giving the supply voltage. So that offered resistance is known as dynamic resistance. That dynamic resistance, that is the ratio of change in voltage by the change in current. That is, you can see over here, RD, dynamic resistance, equal to delta V by delta I. Let us go through the example regarding the same. The VA characteristic of a silicon diode is shown in the figure. Calculate the resistance of the diode at diode current ID equal to 15 milliampere and diode voltage equal to minus 10 volt, as it is available over here in the diagram. That VA characteristic is also shown. So here, the from the characteristic as is available in the diagram, let us take first 10 milliampere current, and then we are moving towards the 20 milliampere current. So that is the limit range we are taking to change in the current, and we can calculate its resistance from using the Ohm's law. So from this curve, at I equal to 20 milliampere, we can see the voltage is available 0.8 volt, and at I equal to 10 milliampere, the voltage is available 0.7 volt. So here, the dynamic resistance in forward bias, as we know now, the dynamic resistance equation is delta V by delta I based on the Ohm's law. So change in voltage divided by change in current. Here we are having a change in voltage V2 minus V1, that is 0.8 minus 0.7, divided by change in current I2 minus I1, that is 20 milliampere minus 10 milliampere. Likewise, the forward resistance we able to get 0.1 volt divided by 10 milliampere offers 10 ohm. Now, from the reverse bias characteristic, it defines that diode voltage VD is minus 10 volt and it generates the current minus 1 microampere. So in a reverse bias condition, the dynamic resistance offered, that is 10 volt divided by 1 microampere, which offers 1 into 10 raised to 7 ohm resistance. So in comparison, we can say that forward bias resistance is very much less compared to reverse bias resistance.